with a review from last time because I think these ideas get a bit dense. So if you remember, we have some sort of a vector bundle which which we denote E over B. So we have some base manifold B, and at every point we have a vector space, and the collection of these vector spaces is denoted E. So E over B is supposed to represent that you have one big space, which is the space of all vector spaces above B, and then this is a projection down to B. And so to sort of add some rigidity onto this, we defined a connection, and the connection was essentially, okay, so I guess first we said like we wanted to compare some vector spaces that were near each other. So we came up with this notion of parallel transport, where if you have some path gamma, then you can define PT, which goes from the, or I guess E sub gamma naught, to E sub gamma T. So basically as you move along the path, it'll give you an isomorphism from this vector space to this vector space, and allows you to compare things. And we sort of came up with an infinitesimal version of this, where we said that if V is a section of E, so if you recall, this means like to every point you assign a vector in E. And if X is a vector field, so X is in gamma EM, so this is a vector field. Then we can take gamma as some path such that gamma prime is equal to X. So basically like just the flow along this vector field X. Then we define the covariant derivative of X of V to be the limit as t approaches 0 of P minus T of V gamma T minus V of naught over T. Okay, so to remind you what this means, we have a vector field taking values in E at every point, and we have some path gamma. And so we want to differentiate this along the tangent vector X at the starting point. And so what we're doing is we evaluate V at this vector space, and what we want to do is take the difference of these two when the two vector spaces are close together. But we can't sort of compare them because they live in different vector spaces. So we use P to take this second V evaluate at the second point at the endpoint of the path and bring it back to our initial point, gamma 0. I guess I should call this PT inverse me. So now they can be compared because they both live in this vector space, and then we just take the usual derivative. So this is sort of telling you that with this notion of parallel transport, how much is your vector changing? So like if you have two vectors like this, maybe like the derivative would be 0 because the parallel transport dictates that those like the vector spaces are compared like this. Or maybe the derivative will be non-zero because like the parallel transport takes like the vector spaces rotate a little bit as we move along. And so I said something a bit wrong last time. So I said that the connection is with covariant derivative is a map from here to here. This is still correct. So this is saying give me a function and I'll give you give me a vector field on E, and I'll give you something where if you give me a vector on your base manifold, I'll tell you how much your vector changes. So that's right, but what I wrote is that gamma V is equal to the sum of AI dxi, or something like this. This is not right, or I guess AI dxi. So this is not quite right because this doesn't involve anything involving the derivative. So what it actually looks like is like in local coordinates. It'll actually look like, maybe I'll just write this. Li equals this, partial I. So if you have some directions x1, x2, x3, x4, and this says that the derivative in the ith direction is just the usual derivative of v in some local coordinates, plus some correction which tells you how to rotate things, like we discussed last time. And so to say this a bit more explicitly, if you have some vector field v, with the vector x having these coordinates, then this will be xi partial ip plus the sum of xi ai. So I'm using the Einstein summation convention where you sum over repeated indices. I guess I don't really need to put the sums here then. So what are these AIs? So A is equal to AI dxi. So it's essentially like combining all of these directional derivatives together is a one form which takes values in G, L, K, R. Which to remind you, this is like, this is saying that E is rank K. And this is like the infinitesimal deformations of a k-dimensional vector space. So essentially this is saying that give me a vector, which is what this omega 1 is saying, give me a vector, and I'll tell you how much the vector space changes. And so if you remember last time we said that if you have two different connections, delta prime and delta, then their difference actually lies in this guy. So neither of these guys do. But this is saying that one of your connections will give you one identification of vector spaces. And if you have another connection, which is another identification, you can say relative to the first one, how much are we twisting? And that's given by these connection matrices. And like we discussed last time, these connection matrices are only defined locally, which is where, or you can define them globally if you have it relative to another connection. But if you have it relative to the quote-unquote standard connection, then this is relative only locally to some local trivialization phi from E restricted to U cross R to the K, which essentially takes each fiber, so each vector space above a point to a copy of R to the K. Any questions on this stuff from last time? Cool. So we also said that if we change local trivialization, so if we pick a phi tilde of x is equal to g of x, phi of x, where g of x is a map from, I guess, our local space to G, L, K, R. So this is full transformations of the thing. So essentially what you're saying is you're rotating each vector space, but you're rotating them differently at each point. Then we saw that these connection matrices get transformed into G, A, G inverse plus G, E, G inverse. So G inverse is like a matrix value function, so it makes sense to say what's the derivative of that, how much is that function changing, and essentially, again, this is to keep this is essentially keeping the derivative the same. If you change how the vector spaces are identified via your trivialization, then you're also going to have to account for that by changing your matrix in the opposite way. So to give a bit more explanation as to what each of these terms are doing, so that you can hopefully see things a bit beyond the symbols, this term is saying, hey, come back to my original frame, then apply this sort of small rotation, and then go back into the new frame. So it's, what is this transformation in new frame in terms of what was in the original frame? So if you pick some G, which is constant everywhere, and that's what this is doing. This is just taking a change of perspective. On the other hand, if at some point G was the identity, then this term would just be A. And so you can look at what does this term do. This term says, okay, I don't change what my initial vector space is, but if G changes as I move my point, then I'm adding an additional twist to how I'm identifying these other vector spaces. So this is somehow to account for that difference and change it back. So to put this in an equivalent way, but in a way that may sort of make that more clear, you can see that d G inverse, this is just equal to the constant identity function. So this is equal to 0. But then this is equal to d G inverse plus G inverse. And so we see that this can be represented by G inverse minus dg G inverse. So it's maybe saying what it is a bit clear. This G inverse is saying go back to my old frame. And this one is saying how much is my rotation at each point changing nearby. And so this minus sign says I have to sort of do the opposite transformation to fix that.
right? So there is some good things and some bad things about this, which is that the fact that we have this extra term means that if we make a change of coordinates, then if a is 0 in one coordinate, in other words, if our derivative is just the standard derivative that we have, then it would be the standard derivative no matter what sort of trivialization we choose. But over here, we have different trivializations. And so one question is, can we sort of simplify our life and find a coordinate transformation which would make it sort of the trivial connection? In other words, a is equal to 0. So that would be, in other words, like solve this equation is equal to 0 for g. Just like a really like seemingly non-trivial equation, right? And sometimes it's possible to solve this equation, sometimes it isn't possible to solve this equation. So today we're going to be talking about curvature, which is an invariant associated to connection. And so I claim that connection sort of gives vector bundle some level of rigidity, and curvature is some sort of way to see that rigidity. So let's say if you put two different connections on a vector bundle, then they will in general have two different curvatures, and that will tell you that, well, the vector spaces are like curving in different ways in some sense. So yeah, if we get to it, then how this relates to cohomology is that we saw that you can't flatten out, or like sort of I pictorially argue you can't flatten out all the vector spaces on a sphere, all the tangent spaces on the sphere. So the tangent bundle on the sphere is non-trivial because again, like if you try to flatten everything out, then on the bottom it gets really curled up. So that corresponds to, in this picture, is saying that to curvature you can associate some cohomology class. And this cohomology class does not depend on the connection curvature you choose. If you choose two different curvatures, then these cohomology classes, or these differential forms that you get, will differ by something exact. So in this case, what we're saying is like we have a total amount of curvature on the sphere, and if we try to flatten out above, then all of that curvature will be concentrated down below. And so we can find some sort of cohomology classes which tell us whether or not we can trivialize our vector bundles. And I will say that trivial connection on the entire manifold corresponds to a trivial vector bundle. So it's a if and only if thing. Because if you have like B cross R to the n, you can obviously find a trivial connection because everything's already identified with one another. And if you can find a trivial connection everywhere, then that also means that you can find like a parallel basis, which means that you can trivialize your vector bundle. Okay. Yeah. So basically, why might you have a non-trivial thing, even if your vector bundle is trivial? That may be because like you trivialize things badly and you just accidentally like rotate your planes in a bad way. So how can you detect whether or not you can unrotate your planes? So we started discussing last time how we can sort of use this idea of holonomy to do this. And the picture that I drew was this guy, where if you sort of walk down here and you point down, and you walk over here and you point down, and you walk up here, then you end up at a different place than you started. So this is saying is that you parallel transport across this path and you end up having a rotation rather than identity. And so this is the principle of holonomy, which says that if you go around a path, then you will in general have you will have a map from E gamma 0 to E gamma 1, but gamma 1 is just gamma 0, it's the same point. So you have an endomorphism of your vector space. And this might not be the identity map. And when it's not the identity map, that means that you have non-trivial holonomy. If you had a trivial connection, then you would have trivial holonomy everywhere because everything's identified in a nice way. So this sort of corresponds to the fact that you might have some twisting of your vector spaces in such a way that if you move around, the vector spaces might twist in a way so that you end up with a different identification at your end point than your starting point. Okay, so our goal is to describe this holonomy. Does that make sense? Cool. So how can we describe a holonomy? So what we can say is, instead of looking at a very big path, let's just look like at a really tiny path. So let's start at this point, and let's move over here in the direction of the vector x, then up here in the direction of the vector y, and over here in the direction of the vector x, and then back down in the direction of the vector y. And so you want to ask, what's the holonomy that we have acquired over here? So it turns out computationally, it's a bit easier to do the following thing. So move along this way from x and then y, and then move up along y and across by x. So I guess what I should say is you have two coordinates. Local coordinates, x and y, on your manifold M. And this leads to vector fields x and y, which is the direction in the x direction and the y direction in the tangent bundle. And then what you want to say is let's differentiate in the let's move in the direction x and then move in the direction y, versus move in the direction y and then move in the direction x, and then see how the parallel transport is different at this endpoint versus the starting point. So to first order, you might imagine that if you start with the vector v here, then what you end up with over here is something like v plus delta xv. And what you end up with over here is v plus delta y of v plus delta xv. Is that correct? Okay, well, what happens when you go the other way is you get a v plus delta y, and then a v plus delta x, v plus delta y. This is not quite right. I think I messed up somewhere. What should happen is that the sort of, let's say that you displace in like some small direction s in each of these. So let's say x and y are unit vectors. So what happened here is you have something to first order. So this will look like s delta xv and s, and then you'll have another s over here, and s and s. So what should happen is that the first order terms will cancel out if you take the difference of these two, which is seeing how much the parallel transport changes as you move in these two directions. So these two should cancel out, so I'll pretend like they do. And then what you end up with is a second order term, which looks like this expression, which is delta x delta y minus delta y delta x of your vector v. Right. So this is saying let me displace in the direction x and then the direction y, versus let me displace in the direction y and the direction x and then see what the difference is. And it turns out to first order, any polynomial that you have vanishes, but to second order, you will end up with this term. Oh, I think the reason that the first order terms vanish is that you're doing some parallel transport, like starting at a different point, and so you would have some first order derivatives coming from there as well. It should be similar computation to like when we looked at the exterior derivative vanishing in the first class. But anyway, so this is your definition of curvature. And so what you define is this thing f mu nu, which is nabla mu minus nabla nu nabla mu. So what this is saying is like if I give you two different vector fields, x mu and y nu, then this will take out all the x components whenever there's a mu, and all the y components whenever there's a mu. So this is saying differentiate in the x and y directions, but you're sort of keeping track of all directions at once. And so this is a true form. Again, with the values of g, l, a, r. Yeah. So what is this object doing? It's saying give me two vectors, and I'll sort of make a little loop in that plane, and then to lowest order, what is the holonomy that I get at the identity, or at the starting point, if I move around in that plane? Does it make sense as to what this is trying to say? And then this sort of GLKR, again, is because that's like an infinitesimal transformation. So if you had no holonomy, then it would just be a identity map. But if you do have holonomy, that would be the identity map plus some small little thing. So that's what you end up with. Okay, so let's compute this. So what we can do is, since we're working local trivializations anyway, we can write our covariant derivative like this, or I guess more precisely like this, and compute what this looks like. So if we look at del nu b, this will be equal to partial mu plus a mu times partial nu plus a nu b. So again, keep in mind, I'm only writing down the spatial indices here, but this is really something that takes in a vector and then it gives you a matrix. But the matrix takes values in E, and the vector that eats up is a vector on your base manifold, which is a tangent vector on X. So if we expand this, we get del nu plus del mu a mu b plus a mu del nu b plus a mu a mu. Okay. So what should we do with this term? This is the derivative of like a product of a matrix and a vector. So I'll give back another vector, right? But what can we do if we have a derivative of a product of two things? Yeah, product both. So this is, I won't rewrite these things, but this guy plus a nu del mu b plus del mu a mu b plus these guys. So this term extends into these two terms. This says I'll apply this sort of rotation matrix to how much the vector changes, and this says I'm going to see how much does the matrix change and then apply that to my vector. And so if we compute the analogous thing for del mu b, what we get is del d, del mu, plus something which looks like this. So this will be a mu del mu plus del nu a mu plus a mu del mu plus a mu a mu, and then all of this acting on the vector. So when you see like this is going to be the product of two matrices, right? What happens is you plug in two vectors, and then once you plug in those two vectors, these will also just become matrices, and so you multiply them, and then multiply these by the vector v. This one, you plug in a vector, becomes a derivative, and then you differentiate v, and then you multiply the result by the matrix, which results when you plug in a vector to this guy. And similarly here, you're taking the derivative of a matrix, then you plug in vectors, it becomes an actual matrix, and then you actor on v, and then so on and so forth. It's a complicated expression, but this is what happens when you expand things. So when we take del nu minus del mu, what is this equal to? So let's look term by term and then see if there's something which cancels it out. So let's start here. I guess I should write it here. Let's start here and then see if there's something that cancels out over here. So does something cancel out this term in this line? Which one? This one, right? Yeah, so because here we're looking at local trivialization, so any derivatives, they just commute with one another, and so these two terms cancel. Cool. How about this guy? Is there something that cancels out with this?
Yeah.
Which one?
Fourth one.
Yeah, this guy, right? So this one will cancel out with this. Similarly, if you look at this term, then this cancels with this guy, right? And so, does this one cancel with anything?
Sure.
What were you gonna say, and what you say, never mind.
They are not derivatives, so they are matrices.
Yeah, so the careful thing to keep in mind is that these two guys are matrices. So when you multiply matrices together, they won't necessarily commute. And so what you end up with is this expression, which is del mu a nu minus del nu a mu plus a nu minus a nu a nu. Okay. Cool, so this is taking the derivatives of these matrices, which will be another matrix, and this one is like multiplying two matrices and writing it out like that. So one thing is we can consider this object A, which is a one form, and what happens if we take dA? So we're gonna have like some derivatives of these guys times this, right? So if we look at the coefficient of dxi, dxj, what we're gonna have is a term which looks like the derivative I of aj, okay? But we're also gonna have a term which looks like the derivative of j, ai, where we swap the sign because we have to switch the terms. And so you can think of A as sort of being a matrix of one forms. And so when you take D, you sort of apply D term-wise inside the matrix. And then you end up with this sort of expression, and this sort of makes sense. This is saying that you take like the derivatives term-wise, and now you end up with like a matrix of two forms. So another way that this is often written is that F is equal to dA. And then what does this term look like? Yeah, so this is a commutator. So this will be commutator of A with A. So this is how it's often written. But really you should think of it just like doing it like this. Like this is something which eats into vectors and gives you a matrix. So the way that it eats into vectors is as follows. So whenever you see a nu, it'll eat in the second vector, and when you see a mu, it'll eat in the first vector, and then you just evaluate like this. Yeah.
What's this commutator thing?
This commutator is just if you have the commutator of A and B, this is equal to AB minus BA.
Oh, okay.
Yeah, so this is similar to what we have over here. So sometimes you'll see people write down that this is this guy.
Okay, it's just shorthand.
Yeah. Yeah, I guess the reason that this is useful sometimes is because here we're assuming that we have something in terms of a matrix, but sometimes you look at things a bit more abstractly where you just have a Lie algebra. And then like matrix multiplication doesn't make sense because you only have a vector space, but you still have a commutator there because of the Lie bracket structure. So you can still define this sort of a curvature in that sense. I think there should there be a factor of 1/2? I don't remember. I think there should be a factor of 1/2, but I'm not sure. Okay. Yeah. So yeah, this is something that sometimes people write, but really you should just think of it as this guy. And so in the problem set that we just had, we were looking at U1 connections, and in U1 everything is commutative, SO2. So it's just rotation, so all matrices commute. And so that means is that these two terms, you can like flip it around and cancel it out. So for SO2 or U1 connections, you get that F is equal to dA. So this is, this is something which takes values in the Lie algebra. I can't draw a math for you. In the Lie algebra of U1, right? And so if you write U1 as e to the I theta, then this will just be I theta. So this is just like an imaginary value function. So this is an imaginary value 1 form, this is an imaginary value 2 form. And so you have this relation. And so what happens is you can actually do something like Stokes' theorem, which we'll see in a second. So again, to recap, we have this F which takes in two vectors and then gives you a matrix, and that matrix sort of represents if you move a little bit along in the plane given by these two vectors, and on your manifold X, how much does your fiber, which is in the vector bundle E, change by? That's given by an infinitesimal matrix rotation. So if you in the special case of U1, then you can actually sort of make that into a larger thing, where if you have some like large loop, then you can show that the holonomy, which is P of gamma 1 minus the infinity, where gamma is this loop, is equal to the integral, or I should say, exponential of the integral over gamma of the connection matrix A. So what does this mean? This is in one form, so we can integrate over a loop. And what this one form is telling us is, as we move along this path, how are we rotating our vector space? And if you so you should expect that if you like compile all of your rotations together, then you get the rotation over the full path. And so because this is like an infinitesimal rotation, what you're saying is infinitesimally what is the angle by which you're rotating. And so what this integral tells you is the total amount of angle that you've rotated. And so when you take this exponential, this is the exponential of I times the total net angle. And so this tells you what the full rotation on your matrix is. So this should be thought as a matrix from a two-dimensional plane to a two-dimensional plane. Right? And here what we can do is we actually have, because of Stokes' theorem, we can say that the integral of, over gamma of A, this solution D, is equal to the integral over D of dA, which in this case, because we're working in 2 dimensions, as I should have said, or not in, but for SO2. And what it means for to be an SO2 connection is that as you move along, you're only rotating, so you can't like scale in any direction. So if we have this condition, then the integral over the boundary is equal to the integral over the area of dA. And this is, as we said, for SO2 connections, is just the integral of the curvature. Okay, so this actually explains, we went over this a little bit in our problem set, but just in the lecture. In the problem session, we saw that on the sphere, we can count the holonomy again, sort of as the angle SS, and we talked about last week how that was because of the exterior angles, some of the exterior angles. And over here, we also showed that the area of a triangle, if this is the angle alpha, beta, and gamma, not gamma, then the area is equal to 2 pi, or no, sorry, what is it? Pi minus the sum, or alpha plus beta plus gamma, which we can check is equal to 2 pi minus the sum of the exterior angles. Okay, so what is this saying? This we showed was the holonomy, and this says that the area is equal to the holonomy. And so what this actually means is that the sphere, in some appropriate connection and some appropriate curvature, which hopefully I'll talk about in Riemannian geometry in a few minutes, the sphere is a space of constant curvature 1. And so this area is secretly the integral over the triangle of f, which in this case is just 1. So this is computing the area, which is just the integral over the curvature. This is computing the holonomy, so this says that the holonomy of your space is equal to the integral of your curvature. So in what cases do you get an SO2 connection? If you put a metric on your vector bundle, which means that you have your base over here, and you have your fibers, E1, E2, and so on and so forth. Then you put a metric on each of these guys, which essentially specifies what the unit vectors are. And so if you declare a connection to be such that the parallel transport has to preserve these lengths, then it can't take values in an arbitrary matrix, it has to take values in SOM. And so if you're working with a two-dimensional vector bundle and you say it has to preserve lengths after you've given lengths to everything, then you'll have an SO2 connection. So that's how you get two SON connections in general. And then yeah, so you have this sort of relation for this guy. So I guess I said that curvature corresponds to an obstruction to your connection being trivial. So I guess I should say that in general, I said that F sort of corresponds to infinitesimal holonomy, and you should think of, in general, a connection as being, the curvature as being sort of something which you can morally apply Stokes' theorem for a general connection. So what I mean by that is, in general, you can sort of hope that the holonomy will be equal to the exponential of the integral over gamma of A. So what does this mean? This is now a matrix valuable in form, but you can still integrate it over some path and get a matrix, and you can take the exponential of that matrix, and then hope that gives you the full holonomy as you go around whatever path that you have. Does this work? Well, almost. The issue is that once you leave this setting of SO2 where things nicely commute, what happens is, how's the exponential defined? It's defined in terms of power series, right? So that means that you're multiplying matrices together, or in this case, multiplying integrals of matrices together. The issue is that when you multiply these matrices, they don't no longer commute. So you have to be careful about the order that you multiply them in. And there is, physicists have figured out, like, or not, I mean, physicists use this a lot more, I think, than math people do. But they have a way of like expanding this guy called like the path order time order exponential, which sort of says that you multiply matrices so that the ones that came earlier in the path are multiplied first compared to the ones that are later in the path. So what this means is that this will look like a sum of a bunch of terms. One of them being something that will look like 1 over 2 factorial integral over gamma of A squared, right? And so what you replace that with is, let's call this the integral from 0 to 1 for simplicity. So what you replace it with is the integral from 0 to 1 of the integral from 0 to t1 of A t1, A t2, B t2, B t1. It might be the other way around. Maybe t2 comes before t1. I don't quite remember. But what this says is that you only integrate t2 from 0 to t1, and then you integrate t1 over the whole path. And you also get rid of this 1 over 2 factorial. And why is that? Well, because you're not multiplying these two guys when t2 is greater than t1. So you essentially gotten rid of half your multiplications. So you sort of get rid of the 1 over n factorial, and you sort of have this series of integrals. So if you had another one, that'd be integral from 0 to t2 for your third term. And then you have an a t3, t3, t, whatever. Right, so you're only integrating t3 from 0 to t2, and then t2 from 0 to t1, and then t1 from the beginning to the end. So you're only multiplying things in the order in which they come. When you look at areas, it's a bit more difficult to do this. So I think though it should be possible to, in some sense, maybe like if you go radially inwards or something, to be able to multiply the matrices in the right way. But like, I don't know if that's true or not, so I'll say morally. What you want to say is that holonomy can also be related to, maybe you have to put an exponential there somewhere, the integral of f over the area which you're considering. So the integral of the curvature over the area which you're considering. Yeah. So what if f is equal to 0? Well, I think in the case f equals 0, everything's fine because everything commutes, so you actually can use Stokes' theorem. But just to be, so morally what you have is that all holonomy is trivial, right? Because you have no curvature, so you have no holonomy on the interior. And so if you start from the beginning to the end, you're gonna get back to where you started. So what that means is that if your connection matrix A was not 0, then you can sort of come up with a potential function, which is pt is equal to the x of the integral from 0 to t of A. And this will be independent of the path that you choose, because similar to what we did in the first week, if you choose 2 different paths, because the curvature is 0, they should give you the same holonomy. And then, quote unquote, you should have the condition that dpt is equal to A. And so that means that you can modify A by this P. You have to I guess you have to multiply it by P inverse. But you can sort of modify A by this guy and then make it 0 if the curvature is 0. So this is similar to what we did in the very beginning, except it's sort of a non-linear version of this because the matrices are non-zero. The way you actually prove it, so I guess I'll say the theorem. Locally, f is equal to 0 if and only if A can be made 0 with suitable change of coordinates G. So this is morally how you would do it. How you actually do it is you sort of straighten out the connection in one direction. So you sort of remove the connection coefficient, say, in the x1 direction. And then you try and straighten out it in the second direction, so you remove the coefficients in the x2 direction. But if you straighten out the second direction, in general what happens is you might mess up what you had in the first direction. But if you have a vanishing curvature, then you can show that straightening out in the second direction doesn't change anything in the first direction. So the way you think about what you mean by straightening out is you have the identifications of vector spaces, right? So you're really untwisting them to straighten them out. But if you have non-zero curvature, then what might happen is as you straighten out things in the vertical direction, you might end up twisting them in the horizontal direction. And that's what this commutator thing is measuring. And if the commutator vanishes, then you don't change anything, and so you can actually fix everything that you have. Makes sense? Okay. Any questions so far on this? So basically, curvature provides a local test as to whether or not your connection can be base trivial. Yeah. So before moving on to Riemannian geometry, I just want to state an interesting application of curvature. So does having zero curvature mean that you always have trivial holonomy? And the answer is no. And so what might happen is, I gave some problems like this on the last set, that if you have a torus, then if you have a loop which goes back to itself and it's contractile, then again you can sort of fill in the curvature is 0, and you can show that there's no holonomy coming from there. But if you choose a path that's not contractible, what might happen is you might pick up holonomy going around this non-trivial path. And if you perturb this path a little bit, say like this, then the holonomy you get from this initial path and this perturbed path will be the same. So it doesn't mean that you get trivial holonomy everywhere, but it says that holonomy is invariant under perturbations. So if you've seen the fundamental group, then what that means is the holonomy of a flat connection, and flat means that f is equal to 0, induces a map from paths to G, L, and R, or K, R, where K is the rank of your vector bundle. So this is true in general, but if you have a flat connection, then that means that this is invariant under homotopy. So it actually gives you a representation of pi 1 of x to G, L, K, R. I'll actually just replace this with the group G. Because sometimes, for example, if you have an SO2 connection, then you'll actually have a holonomy to SO2. And I think the theorem is that flat connections up to gauge equivalence. Gauge equivalence means these change of coordinates that we were working with earlier, because if you like change coordinates, you're not really changing the connection, right? So if you look at phi connections, or like the connection matrices up to these change of coordinates, then this is, I think, in one-to-one correspondence with maps from I1 of x to g, modulo g, where this acts by conjugation. And so the point is that you don't have, you're sort of making a representation by making like, you can think of it as like putting a vector space structure, or putting a basis on your initial point and seeing how that basis changes. But because there's no canonical basis that you can choose for your initial point, you have to quotient out by this conjugation action. So you get like something representation theoretic related to something in differential geometry. And this is pretty interesting. It gives you some like subtle invariance, I guess, of your manifold. And you can sort of think of this as like a non-linear, or sorry, a non-commutative generalization of the first homology. So if G is equal to SO2, then what happens is that this guy just becomes, because G is now abelian, this will factor through H1 of x, comma, SO2, and I'm going to ignore, this is technically integral homology and cohomology, but I'm going to ignore that. So this then becomes so you have the dimension of H1 many generators of the homology, and you have a circle for each one of them. So I think that this should be equal to H1 of x modulo H1 of x with z coefficients. So what this is it's a torus. Instead of being like a vector space, you get a torus. But the dimensionality of the torus will be the same as the dimensionality of your first cohomology. So this essentially covers the first cohomology. But if you have a non-commutative group, then you can get some non-commutative understanding of your fundamental group, which you can get from homology or cohomology. So this is some sort of like a non-linear or non-commutative generalization of that. And one of the directions in which this goes is something called non-abelian Hodge theory. I guess since we're coming to the end of the class, I just wanted to state some interesting things that you can do with this, so if you're interested in later. And non-abelian Hodge theory, what it does is you take a complex vector space, and there's another notion of rigidity that you put on your vector bundle called making, you take a complex vector bundle, which is just complex vector spaces instead of real vector spaces, and you can make them into holomorphic vector bundles, which means something complex in geometry. And that's related to these flat connections, not actually flat, something called projectively flat connections. Optic gauge equivalents are equivalent to this algebraic geometry structure. So you can relate like algebraic geometry or differential geometry and then do some interesting interplay there. There's this paper by Atiyah and Bott where they use something about Yang-Mills on surfaces to compute the space of holomorphic vector bundles, which is it's really complicated, but it's I sort of want to give a sense of like, this is something that's actually useful and actually used, and I feel like maybe connection and curvature, like where differential forms start to enter into real problems that you can look into, because it sort of gives you some rigidity, which means that you can start doing some sort of geometry. Another place that this happens is Donaldson theory. So we discussed the Hodge star earlier, and on four-dimensional manifolds, the Hodge star is a map from H2 to H2, such that Hodge star squared is equal to 1. So you can decompose H2 as being these two subspaces, H plus H minus. And these are the subspaces where the star gets equal to itself and the star acts by -1. So an example of an element in H plus is dx dy plus dz dw, and an element of H minus would just be replace this with the minus sign. So if it's plus, then swap these terms, the Hodge star. If it's minus, they'll swap these terms, they pick up a negative sign. So that means is that the same thing applies to curvature. So because curvature is a two-form, you can decompose the curvature into the self-dual and anti-self-dual parts. And you can look at things called anti-self-dual connections, which are connections which have the self-dual part of the curvature equal to 0. And there's an interesting fact about these anti-self-dual connections, which is that you have a total curvature. So I'll just put that in quotes. In actuality, what this is the term class. I think the second term class. So you have some total amount of curvature, which has to be sort of distributed along your manifold. So it's kind of like when we said that we can push along the curvature of the sphere down to the bottom. So that's the same sort of idea over here, that you have a finite amount of curvature and you can sort of push it around your manifold. And the equation for this is that star f equals minus f. So this is some differential equation of your connection. And it turns out that the space of solutions to this equation is some finite dimensional manifold. But it's a non-compact manifold, and the reason is that what you can do, what happens is that if this is your space X, then you can have a curvature which starts off over here, and then sort of modifies so that curvature gets more and more concentrated. And so the curvature sort of starts to build up near a point. But it never actually gets to that point because you can't have curvature located at a single point. But if you like sort of generalize your notions, then you can have curvature located at a single point, and then this sort of corresponds to L2 connections or whatever. And so you can compactify your manifold, and it turns out that when you push all your curvature to a single point, the amount of curvature at that point has to be like also some, this is, by the way, this is basically some integer multiple of like 4 pi squared. And the amount that you take away also has to be some integer multiple of 4 pi squared. You sort of give some amount of curvature to this point, and give some amount of curvature to this point. And so you can sort of iteratively build up a boundary structure for this manifold. And you can study that manifold. And that was a lot of words, but what this tells you is if you analyze this enough, you can find examples of manifolds which are homeomorphic but not diffeomorphic, which means that like the calculus on them or the solution to the differential equations on them are not the same. And that essentially comes because the solutions to these differential equations are not the same on both manifolds. So that's another interesting application of curvature and connections. Let's see. Yeah, I think I can discuss Riemannian curvature in 10 minutes and then do Gauss-Bonnet in 10 minutes. So let's do that. So let's talk about Riemannian geometry. So if you remember, I had this sort of picture where I said, say you put metrics on each of your vector spaces. And this is now working on E is the tangent bundle to our manifold. So this is saying every vector on our manifold, we're going to give it a length. But in this picture, sort of these ones are stretched out, so you might have to like compress them a little bit to make them all look the same. So eventually what might happen is your manifold might look like this, so that all of these vectors actually look the same length. So again, like look the same is based on what I drew on it. So what I should mean by look the same is I should compare the vector spaces in some way. And now we've developed a theory of how to compare vector spaces. So there should be some connection given to us by the metric that we put on our manifold that will allow us to sort of compare vector spaces and say whether or not they look the same. And then it turns out the curvature of this manifold is this notion of curvature on, it agrees with this notion of curvature on surfaces. So on surfaces, you have this notion of curvature where if you have something that looks like a dome, it has positive curvature. If you have something which looks like a single chip, it has negative curvature. And then if you have something which looks like a cylinder or a piece of paper, it has zero curvature. Turns out this will agree with what I'm about to describe. So given metric G on this guy, we can construct this delta, which I'll call Levi-Civita. It's called the Levi-Civita connection, and G uniquely specifies this Levi-Civita connection. So how does it specify it? So it has to, one, be metric compatible. So I've already discussed this condition, which says that if you do your parallel transport, it won't change the length of anything. But that's not enough to actually uniquely specify connection, because for example, say you take a line segment, and you have a bunch of these vector spaces. Well, if these are all like sort of the unit lengths, the unit vectors all connected to each other at parallel transport, you can sort of still twist them around and still have it be a metric compatible connection. Which I should also say as a side remark, you should sort of imagine that if you do have a one-dimensional manifold, then you can always straighten out your vector spaces, right? Because you know just like rotate them in the right way. And in fact, there's no two form on a one-dimensional manifold, so the curvature always vanishes. So that means that because of this local obstruction theorem, it actually does tell you that on a one-dimensional manifold you can always straighten things out. So what might happen on a manifold is, on a higher dimensional manifold, let's say that you want to move in this direction and then see how your tangent vectors are parallel transported. So it sort of makes sense that like if you take the tangent vector, if this is like a straight line, quote unquote geodesic, then you should sort of move the vector in the direction that you're walking, right? But then what about this vector perpendicular to it? So you might like move it like this, but you might also like sort of rotate a little bit into the page or something, right? So there's a little bit of ambiguity over there. You can either like move it like this, or you sort of rotate it around like this. So what's the correct thing to choose here? So what you want to happen is, say this is a curve diagram, and if I sort of parallel transport everything along up here, or sorry, so this is the initial vector that I'm moving along, right? So this is the vector field x. And if I parallel transport y, so this is y, and these vectors are p parallel transported along x of y, okay? And then what I can do is I can then parallel transport x along these vectors. I'll get some other vectors like this. And what is the condition that I want here? Ah, no, I forgot it. Yeah, I think, hold on, new picture. Okay, so you have two vector fields. You have your vector field x, which you're moving along this way, and you already have a vector field y, which is sort of another coordinate vector field. So this is your vector field y. Or what you can do is you can parallel transport in the direction x of your initial vector y0. So this vector over here, this one is y0. And what you can do is then you can sort of trace out the tip of both paths. So the first one should be another coordinate piece, which is just the x-axis like translated up a little bit. But then what you want to avoid is in this case, what I drew is that this parallel transported vector will be rotated around some amount. So that's what we want to avoid. It's essentially the same rotation that I said over here, except in this case you sort of say which things aren't rotated by saying that coordinate patches, like coordinate functions, aren't going to be rotated. And so this is a condition called the torsion-free condition. It says that parallel transporting coordinate vectors gives coordinate vectors. So you don't get some sort of twisting involved. And if I had like 10 more minutes, I would talk about the Lie bracket, but I don't want to. So I'll just write that the condition over here sort of looks like this. And what is this? So you can consider x and y as vector fields acting as differential operators, where you sort of differentiate the function in the direction of x and y. And so this is the same thing that we saw before, where you first differentiate y and then differentiate x and then subtract the difference. It turns out this is 0 if your vector fields come from coordinate patches, but it's non-zero in general. Because, for example, you might have the vector field y looking at 0 over here and then growing like this, and the vector field x moving horizontally. So if you go like x, y, minus x, but then if y is like 0 in this direction, then you don't go back down. So the commutator will sort of point up. So it'll be non-zero. It'll be 0 if and only if you can find a coordinate patch or define coordinate functions such that these vector fields come from those coordinate functions. And so this is the condition of torsion-free. And then given the conditions of metric compatibility and torsion-free connection, there's a unique connection that this induces, which sort of makes sense. It's saying that you're preserving length and you can't twist anything, so it should uniquely identify it. And I won't write the formula down because of time. But then you get this connection over here. And the curvature that comes from that connection is called the Riemann curvature. So this is usually written R, A, B, C, D. And so these two vectors are the vectors that you're feeding in, which is saying rotate in the plane that defined by the C and D vectors. And this one is saying what's the linear transformation at the starting point from B to A. And so this is the curvature that you get. And it turns out in 2D, this is specified by one number, which is called it's just called, I'll just call it curvature. Sectional curvature or whatever. But there's just one number in 2D, which is that number that I previously stated. So we need to explain that in a minute, but I want to, instead of doing that, explain a bit more interestingly this theorem called the Gauss-Bonnet theorem. And I guess this is technically global Gauss-Bonnet theorem. And so this curvature is called K. It's a single number. It turns out that if you have a two-dimensional manifold, then this entire complicated thing can be written in terms of functions of this single number. And the Gauss-Bonnet theorem says that the integral of the curvature over your entire manifold M is equal to 2 pi times the Euler characteristic of M. So this is something that has to do with curvature, and this is something that has to do with topology. So this proves for you why you can't straighten out the sphere, because if you would be able to straighten out the sphere, then you'd be able to get zero curvature on this side. But on the right-hand side, you get a non-zero number because the Euler characteristic of the sphere is 2. So yeah, this gives a topological obstruction. So we can prove this. So proof. I'll start with proving it in S2. What we can do is split the sphere into 8 of these triangles, which have right angles at each end, right? And so if we take the integral over the manifold of the curvature, this is the integral of 1 over the entire manifold, because this is a one-dimensional thing. Or I guess this is just giving you an idea in this special case as to why this is true. And we saw that on each of these triangles, so there are 8 of these triangles, and each of these triangles is equal to the area of the triangle, and the area of the triangle we saw was pi over 2. So this will be 8 times pi over 2, which is the angle excess, so this will be 4 pi. And I guess you could just integrate 1 over the entire sphere directly, but what I want to show with this was that you can sort of understand this integral in terms of the holonomial. And this allows you to prove it for higher genus surfaces in a similar way. So what you can do is for g greater than or equal to 2, you can take a decomposition of your surface into 4G many loops, which will look something like this. And it turns out that you can actually describe these guys, or actually, let's say this. So all these loops meet at one point, right? And there's 4G many loops, and they all meet at this vertex. So if we were to write this sort of as a polygon, then this is not an accurate picture because the angle sum over here is going to be greater than 2 pi. But because you're identifying all the vertices together, the angle sum needs to be 2 pi. So what that means is that if this is alpha I, then in a more accurate picture, the sum of alpha I should be equal to 2 pi. Now it turns out that you can actually sort of curve these lines a little bit and have an octagon that kind of looks like this. And it turns out that because these are all pinched in a little bit, that you can actually make it construct it so that the angle sum is equal to 2 pi. Yeah. So this may not seem like a polygon, but it turns out that it is a polygon in hyperbolic space, which is why I decided to wear this t-shirt. So you can prove that you want something where the exterior angle is equal to 2 pi, right? So for example, that could mean that each alpha I is equal to 2 pi over 4g. 2 pi into 4g minus 2 over 4g, right? This is the total interior angle sum. Wait, is this right? No. What do I want to see? Yeah, this is right, right? So you have 4g many sides and you need that the sum of the angles is 2 pi. So you want to find a polygon in here with these hyperbolic circles so that the angle sum is equal to, or is that each angle has this property. So you will notice that for g greater than 2, greater than or equal to 2, but this is greater than or equal to pi times g yeah, 4g minus 2. Okay, so what is this saying? This is saying that this is the polygon sum in a usual polygon, right? 4g many sides. This is saying distribute those all to each angle. This is saying that the angle over here, sorry, this is less. So this is saying that the angle over here is smaller than this. So why does that help us? Because in the hyperbolic plane, you can sort of start off with this ideal polygon, such that each corner has an angle of 0. And if we sort of shrink this guy to be really, really tiny, then it'll look like a classical Euclidean polygon, which has an angle sum really close to this. So by the intermediate value theorem, you can find a polygon which has each angle equal to this. And it's really convenient that this works out for g greater than or equal to 2, because if you plug in g equals 1 exactly, then these two guys are equal. And I'll explain why that's interesting in a moment. But once you can do this, what you can do is you can say, okay, well, we can compute our integral of curvature over the entire manifold M as being the integral, or as being the holonomy over this 4g norm. Right? Okay, so what's the holonomy, as we said? It was 2 pi minus the sum of the exterior angles. Right? And this is equal to 2 pi minus the sum of pi minus alpha I, which are the interior angles. And so you have 4g many, is correct? I think so. Yeah, you have 4g many sides. So this will be 2 pi minus 4g pi. And then the sum of the alpha i's is equal to 2 pi. So you get a 2 pi here. What you end up with is 4 pi minus 4g pi, which is equal to 2 pi times 2 minus 2g. So you just proven Gauss-Bonnet using some nice polynomial argument. So if we were for S2, quote unquote, what you can do for S2 more specifically is like split up into a bunch of polygons and then apply holonomy for each one and then stick them all together and prove it that way in general. And then for T2 you can do the same thing. And as a special example, what you can do is you can quotient out the plane by squares, right? And on a square you have zero curvature. And if you look at the angle XS, the holonomy is also trivial because the angle XS is 2 pi. And so that similar technique sort of prove for the torus as well. So this is interesting because the reason I said this was cool that this only works for g greater than or equal to 2 is because you can't put a hyperbolic, this induces a hyperbolic metric on these manifolds. So on these manifolds, the metric, so what it means to have positive curvature, like on a sphere, is that if you start with two lines that are near each other, you sort of come closer together, right? On a sphere, that's what happens. On a space like this, what happens if you start off with 2 points close to each other, you sort of diverge from one another, right? So it says that on a surface, you can always put a metric such that lines tend to diverge from one another. But that only for g greater than or equal to 2. For g equals 1, you can't do that, but you can put a metric such that things are always parallel. And so it says because this is negative curvature and the total integral has to be negative. So this is only possible if g greater is equal to 2. And for the lines to always be parallel, this is only possible if g equals 1, because that's when the Euler characteristic is 0. And for things to always come together, this is only possible when g is equal to 0, because then the Euler characteristic is positive. So this sort of tells you that the sort of like uniform structures are actually restricted by this relationship over here. So I guess in like 5 minutes, I'll try going over another proof of this theorem. So the other way that this theorem can be proven is it turns out that in R3, the curvature can be described in the following manner. So you take your torus guy or whatever surface in R3, and at each point you have an outward facing normal vector. And so you use that outward facing normal vector to have a map to the unit sphere, right? This is your outward facing normal, and then this point gets mapped with this point, and so on and so forth. And so what you have is this map over here, which is called the Gauss map. So I'll call it G. And so the determinant of G at some point P, or I guess I should say the Jacobian, which is going to be a single number, is going to be equal to the curvature at that point, turns out. In general, there's like some relations to relate the intrinsic curvature, as I defined it here, to the extrinsic curvature, which is how your manifold is embedded in your larger manifold. Turns out for a surface in R3, they're the same thing. So what happens is if you have a sphere going to the sphere, then this sort of wraps around it once. And so when you take the integral of kp, you're going to get 4 pi, because you're sort of integrating the determinant of the Jacobian map on the image, and the area of the unit sphere is 4 pi, so you get an integral of 4 pi. What happens if you map the torus to the sphere is that this outside part is going to contribute 4 pi, but the inside part, which is sort of negatively curved, is going to contribute a minus 4 pi, turns out. So this is sort of going to cover it positively, in the sense that if you move this way, it'll cover the sphere in that direction. But this one's going to cover it negatively, in the sense that if you move like this, because the outward facing normal over here is this point, and if you move a little bit more this way, then it's actually going to move in the opposite direction. So it won't move that way, it'll actually move the other way. So this will cover it once negatively. So it's going to be a minus 4 pi in the integral. And if you take a genus 2 surface, then this outside positively curved part will contribute a 4 pi, and each inside negatively curved part will contribute minus 4 pi. So that's why you get sort of a minus 4 pi each time you add a whole space. So how can you sort of prove that rigorously? Well, you should sort of see that this is sort of talking about how many times we cover the sphere. So this should be related to like a degree map, right? So we're essentially saying that the integral of the curvature is equal to degree of the Gauss map. And so we saw in like the linking problem set that there's 2 ways of computing the degree. You can either take the area form on your resulting manifold, and integrate that, the preimage of that, which is essentially what we're doing over here. Or you can like put a form at the very top point and pull that back and then count the number of preimages. So we want to count, for example, if we have a torus embedded into R3 like this, we want to count how many times is the outward normal pointing upwards, right? And it turns out to be a bit easier to count how many times you have either an upward pointing normal or a downward pointing normal. So what you can do for this is, also I guess if you have like a genus 2 surface, then another piece of intuition is that this top and bottom point will be positively curved, so you get +2 pi contribution for each of those. And each of these intermediate points, which have an upward downward facing normal, have a sort of look like your Pringles chip. So you get -2 pi for each of those. That's another reason why this equality holds. But one way that you can detect these is you can put this vector field on your manifold or on your surface, which sort of is the downward flow of the height. So the way I saw this described in one book was like a honey flow. Like you put honey at the top and it's gonna like flow down and you like sort of follow the path at which that flows. And each of the critical points is gonna correspond to something where the honey doesn't have a preferred direction. In other words, a point where the you have a normal vector. Okay? So what we have is, based on embedding into R3, we have this height map. And if we look at the gradient of the height map, which gives us this vector field, then the singular points of that vector field will give us the degree of the map to the sphere. And we proved earlier, or I gave a sketch of a proof earlier, that there's a theorem called the Poincare-Hopf theorem, which tells you that the number of vanishing points of a vector field is equal to the Euler characteristic. So in this case, the degree of the Gauss map, which is again equal to the integral of the curvature, is equal to I of m. But because this is the degree, we have to, so we're actually trying to pull back a form which has a total area of 4 pi, but the degree was things which have an area of 1. So we have to scale this by 4 pi. So this is off by our actual answer by a factor of 2. Does anyone see where that factor of 2 comes from? So I'll give you a hint. When we're looking at degree, right, we're only looking at things which map to the topmost point. In this case, we're looking at the top and bottom, right? So, and the reason for that is kind of because it's hard to like figure out when the normal vector is pointing upwards, but it's easy to know when the normal point is pointing vertically. So it's much easier to detect top or bottom versus just top. And so again, we saw like in the linking problems that we did, that if we look at the intersections of two guys, we can either look at them like when one is above the other or vice versa. And we took a form which was like 1/2 at the top and 1/2 on the bottom. So that's essentially how we're counting degree over here. So this should be pi over 2, which gives us a proof back. So this is sort of nice because it's a pretty big theorem. It says that the integral of the curvature, which is another geometric quantity, is equal to something purely topological. And we've seen like proofs of this which involve like basically everything that we've done so far, except for algebra. Using like degree maps, using like coverings, and even using ideas from holonomy and curvature. So yeah, I guess it's probably a good place to stop.